Okay, you need to be reading section 7.3 on dot structures. So we're going to wrap up covalent bonding today, just introduce dot structures. And then the prepare to learn for dot structures is due tomorrow night, midnight. Remember, that's just the quick 4-point assignment, give you a chance to look at the book and look at the page on Canvas that has the objectives, so you know what we're getting ourselves into. We'll have a homework assignment on dot structures due Sunday night, so you have a chance to practice this. And then I plan on having a quiz on Wednesday. I will probably assign an additional homework assignment with more complex dot structures that will be due sometime next week, but it may not be due before the quiz. I highly recommend you at least try it before the quiz, because I'm going to go into all kinds of dot structures on the quiz. Okay. Questions? All right. So we had spent the time on last week talking about different types of bonding. And we had our ionic, our metallic, and our covalent. So with the covalent bonding, that purely covalent nonpolar bonding is kind of the extreme end of two nonmetals bonding, and it's the opposite of ionic, which is a metal and a nonmetal. So I have a positive charge and a negative charge that are attracted to each other. And we said the thing that keeps the covalent bonded atoms together is that they're sharing electrons. And so we have this gray area in the middle about how much they attract the electrons. So in a polar bond, one of the atoms attracts the electrons more than the other. And that's dependent upon electronegativity. So we have oxygen here being very electronegative. What's more electronegative than oxygen? Fluorine. So if we ignore the noble gases, which we usually do when talking about electronegativity, fluorine is the most electronegative atom. And rather than trying to memorize numbers or having to look them up every time, we're just going to use the periodic table to say how close is this element to fluorine. And the closer it is to fluorine, the more electronegative it is. Now, if you're having to compare something that is to the side versus down, the electronegativity drops off faster as you go down. So the ones that are at the top tend to be more electronegative than the ones further down, if that makes sense. So if I'm comparing oxygen and chlorine, oxygen is more electronegative because it's higher up than chlorine is. So that tends to be the case. Okay, we talked about the definition of electronegativity. You should have this in your notes from Friday. That because with electronegativity, we're talking about the sharing in a bond, in a covalent bond, we're usually comparing the electronegativity of one atom to another or one element to another to know how much sharing is going on. And then we talk about if there's a really big difference in electronegativity, we call that an ionic bond. And we'll take a closer look at that in just a minute. Your book kind of gives you some defining points. What I'd like you to remember is that if it's a metal and a nonmetal, it's ionic. If it's two nonmetals, it is covalent. And then, of course, if it's two metals, it's going to be metallic. And then just remember that most bonds are going to fall somewhere between purely covalent and purely ionic. They're going to have some ionic character, some ability to separate into ions, and some covalent, some sharing of electrons. For our purposes, we'll kind of treat them as if they're either covalent or ionic, but there will be points later on in the semester where it becomes important that sometimes both descriptions of the bond are appropriate. Okay, so getting back to this, how polar is polar? If I have a purely ionic interaction, remember I'm just attracting a positive thing to a negative thing, and there's not really any sharing in between. And so what we would say about the electrons is that the electrons spend all of their time around the anion, and the anion would be the more electronegative because the anion is going to be the nonmetal. Nonmetals tend to form anions, and since it's more electronegative, it's just going to hang out over there and not spend any time at all over on the positive. So that would be purely ionic. And the reality is there's no such thing as purely ionic. That electron's going to be at least a little bit attracted to the positive on the other side. So polar covalent, this is some notation that you need to be familiar with. And so I've indicated this on the Canvas page for this chapter, that you need to know these symbols. So you need to be familiar with these. So on the left and the right-hand side, there is what kind of looks like a figure 8. What it is the lowercase d in Greek. So delta in Greek is a triangle. The capital delta is a triangle. The lowercase kind of looks like our lowercase d if we put a curve into the stem instead of making it straight. So this is the lowercase d. Get that down so you can see what I wrote. Okay. And then we indicate whether we're talking about the partially positive side or the partially negative side with a plus or a minus. Okay. So what that means is I don't really have an ion on the left and an ion on the right. I have something that, as I approach the molecule, looks like it's positive on one side, but it's not going to separate off. Okay, so it is partially positive. If I'm approaching the ion from the other side, it's going to look like it's negative. And so it's going to be attracted to positive things around it, but it's not really going to separate off of the rest of the molecule. So we say that side is partially negative. So this means partial. Partially negative, partially positive. So that's one way that we can indicate the polarity of a molecule, which direction the polarity goes. And the other way we can do that is with an arrow. And so arrows in chemistry have very specific meanings depending on their styles. As we get into dot structures, we'll talk about some other arrows that have some specific meanings. But in this case, you'll notice the arrow has a little cross at one end so that the end looks like a plus sign. So that indicates that we're going from the positive where that plus sign is, and then the arrowhead is showing you where the more negative side is. Okay, so the arrow points in the direction of the more partially negative part of this. So we can show the polarity of just a single bond, and in the case of this molecule, the bond is the molecule. We can also show the overall polarity of the molecule. In a couple of weeks, you're going to be using a program in lab that is going to allow you to look at the polarity. And so you'll be looking for an arrow like this to indicate the direction of polarity. Okay. And then we have purely covalent. Now, technically, the only non-polar bond would be between identical atoms. So hydrogen, hydrogen, oxygen, oxygen, those kinds of things. What do we call elements that most commonly bond in pairs? Diatomics, okay? So if you had me last semester, you know that I wanted you to list those or to memorize that list of 7 diatomics. On the Canvas page, there is a page called Molecules to Know. And the first set is the diatomics. For me, the easy way to memorize it is from the periodic table. So tilt the screen up here and get this out of the way for you. If we look at the periodic table, we see these green and light blue elements are our nonmetals. There is a dark green and a light green, starting with nitrogen, going over to fluorine and down to iodine. And that kind of looks like the number 7. Okay, there are 7 diatomics, and it includes those 6 plus our problem child. Who's our problem child? Hydrogen, way over there. Okay, those are the 7 elements that are going to form diatomics. So that's important to know because sometimes you'll be reading a question and I might just say oxygen and I don't say O2. You need to remember that oxygen is O2, okay? Those are the ones that are going to have non-polar, purely covalent interactions. Now, your book describes anything with an electronegativity difference of 0.4 or less as being purely covalent. We might consider those to be slightly polar. So as long as they're different elements, they're slightly polar. And the best example of that is carbon and hydrogen. Carbon and hydrogen are elements that are found throughout organic chemistry. And the fact that their electronegativity difference is so small means that almost all organic compounds that are made of, well, I think all of them that are made of carbon and hydrogen are non-polar molecules, okay? So that's really kind of significant when we're looking at that. So when I ask a question on a test, if I say purely non-polar, I mean, it has to be the same element. If it is 2 different elements, it's got to be a little bit polar, okay? And if you want to distinguish between polar versus slightly polar, that's fine. But if I ask on a test or a quiz, it has to be the same element to be considered a non-polar bond. All right, so here is another way of looking at the electronegativity difference and the polarity. And so your book uses the difference of 1.5 as being kind of the cutoff for what's considered ionic versus covalent. And so you notice as you go from left to right across the bottom, we've got the delta En. Delta means change or difference. That's the difference in electronegativity. And so right when I get to 1.5, that's where I'm seeing almost every single combination that they have is above that line of ionic, okay? The midway point of ionic versus covalent. So we have those differences. And then if you pay attention to the elements that are in combination there, and I'm going to turn off the light up here so you can see the writing a little better. The combination of elements on the top, they're going to be metals and non-metals. Okay, so we have lithium chloride, we have potassium chloride, we have calcium chloride. Cesium chloride. We have potassium bromide, okay, metal and non-metal. That's what I want you to have in your brain, okay? Metal and non-metal, that's going to be an ionic compound. And you'll see the one that is a little bit higher difference in electronegativity, but falls below that sort of 50% covalent versus ionic, that's 2 non-metals, hydrogen and fluorine. And because those are so small, they do a little bit of weird things. Hydrogen's our problem child, we know. But for the most part, when we combine hydrogen with other non-metals, we're going to see more covalent interactions there. All right, so let's look at B, the second side, the right-hand side. What this graph is showing, these sort of chopped off cones, is the electron density. So what do we mean by electron density? So we think of electrons as being tiny little spheres that are kind of zipping around the outside of a nucleus. But we also know that electrons can behave like a wave, right? That was the whole idea behind the whole quantum mechanics that we did last semester and looking at light and calculating things about waves and whatnot. Electrons sometimes behave like waves, and that's how we get to orbitals and talk about orbitals and those kinds of things. So what this electron density is showing is what is the probability of finding my electron in that space. So you can kind of think of it as where is the wave big? Or you can think of it, if I took 1,000 snapshots of this atom and could pinpoint where that electron was, where would it be at all those points and then kind of add them up? So where the cone is very high, you have a very high probability of finding that electron. And where it's very low, you're going to have a very low probability of finding that electron. Both of these elements have core electrons. So we're seeing that they both have electrons very close to the nucleus. That's why it's very high right where they are. But what we want to pay attention to is, are there electrons that hang out in between the two? And you'll notice the arrow pointing down to the bottom there, it says the overlap indicates some electron sharing, but it's barely overlapping at all. Those two circles are just touching one another, okay? So this is between lithium and fluoride, a metal and a non-metal. And so this is an ionic interaction, but like I said, it's not going to be purely ionic, because nothing is purely ionic. So there's a tiniest bit of sharing, but for all intents and purposes, they're not really sharing, okay? Now, that's an ionic bond. Now let's look at some covalent bonds. So hydrogen-hydrogen, purely non-polar covalent. Fluorine-fluorine, purely non-polar covalent. Those two are diatomic molecules. And so they have equal sharing. Now, fluorine has more electrons than hydrogen does. So the cones are bigger because you're more likely to find an electron in a given space. But they both have a significant overlap in the middle. Instead of that dip going all the way down to the ground where it's practically zero, that dip just kind of goes down a little bit in the middle. Okay, so since that meeting point between the two isn't all the way down at the bottom, it's somewhere up above the ground, so to speak, that means that there's covalency, there's sharing going on. Okay, where that minimum is, if you've had calculus, you talk about a local minimum. So where the minimum of the dip is, the bottom of the dip, if it's smack dab in the middle between the two nuclei, we say that is non-polar. So that's what's going on between the two pairs on the left and middle. But if I put together a hydrogen and a fluorine, that dip is no longer, the center point of that dip is no longer smack dab in the middle. It's kind of shifted over. Okay, and so the bottom of that dip is closer to hydrogen, which means that fluorine, the most electronegative one, is gathering those electrons a lot closer to itself and holding on to that electron a lot more. Okay, notice the arrow that is on there. Okay, that is our polar arrow, and it's indicating that the electrons are more to the right-hand side than to the hydrogen, and the little plus side is on the hydrogen side. Okay, so while hydrogen is a non-metal, it is in column 1 for a reason, and that reason is that when it interacts with most non-metals, it tends to be more positive in character. And it does form a +1 charge. All right, so we can talk about whole molecules. If I'm looking at the water molecule, oxygen being right next to fluorine, very electronegative. And so it holds on to the electrons more. It's precious electrons, so the oxygen attracts the electrons more strongly than the hydrogen. And so because of that, it's polar. So we've got the water molecule kind of looking like a family doing some ice fishing here. And of course, ice fishing is more popular in the polar regions where there is more ice. And so water is a polar molecule. All right. Questions about polarity? Okay, so this kind of sums everything up. Covalent versus ionic. Now we also kind of in the back of our mind have metallic, but we don't really talk about metallic because don't make interesting molecules for Gen Chem with metallic. So one difference is the electronegativity. Covalent bonding, small difference in electronegativity, tends to be less than about 1.5. Ionic, a large difference in electronegativity. For covalent bonding, we have a significant overlap of electron density. And that was that cone-shaped thing where the dip was very high in the covalent bonding, and in the ionic, it was almost as if it went down to 0 between the two. And so if I have significant overlap, that means I've got significant share. If I have minor overlap of electron density, I have very little share. So the result of this is that covalent interactions are found most commonly in molecules. Nonmetals tend to form molecules. But ionic interactions tend to result in crystals. Now, when we talk about the energy of an interaction, we're talking about how much energy do I have to put in to separate those two atoms. And that could be in a variety of ways. I could put in electricity, I could heat it up with fire, I could use kinetic energy, but I somehow have to put energy in to pull those atoms apart. And you might think that for an ionic interaction, it would be the highest, and it is pretty strong, but it is not nearly as strong as a covalent interaction. Now, there is some overlap depending on which ions and which molecules you're talking about. But for the most part, covalent bonds are very difficult to break, and ionic bonds, if you think about it, if you can dissolve something in water, it just takes a little polar molecule to get in between those two atoms. Okay, so I didn't have to put in the energy of a flame or electricity in order to separate those. And probably the most important thing to remember is that for a covalent bond, I'm going to have two nonmetals. And for an ionic bond, I'm going to have a metal and a non. All right, so this is looking at the interactions of chlorine with other elements in the same row. So period 3 on the periodic table. And we've got a picture of those combinations, and we also have some graphs. So the first graph at the bottom I want to look at because it talks about the difference in electronegativity. Okay, so if I'm comparing the two that are farthest apart, sodium and chlorine, they have an electronegativity difference of 2. Okay, and so that's the biggest one here. And you can see there's a pretty steady change going to across the table, getting smaller and smaller and smaller until the two chlorine atoms, obviously there's no electronegativity difference there. All right, so first thing to notice is that there's no one place where it's very, very different in the difference in electronegativity. There's no one place where you can say, clearly that's ionic versus clearly that's covalent. We talked about that kind of range, that gray area where you have, it's got some polar character and some ionic character. So what happens when we look at some other properties that might tell us whether or not it's acting ionic or covalent? So let's take a look at the pictures. You'll notice the first 3 jars there contain solids: sodium chloride, magnesium chloride, and aluminum chloride. Okay, so ionic compounds tend to be solid at room temperature. They form crystals, and the reason for this, it's a little counterintuitive based on what I had just said before. The covalent bond is very strong, but from one molecule to the next molecule, that's pretty weak. Okay, so one water molecule to the next water molecule, that interaction isn't nearly as strong as a positive versus a negative. Okay, and so that stronger ionic interaction keeps those in the solid form. The individual molecules then can be attracted to one another if they're polar. So if they're polar and we have positive sides and negative sides in our, let's say our phosphorus trichloride, the negative side is going to be attracted where the chlorines are. That's going to be attracted to the positive side on the next molecule. So that's going to keep those molecules kind of close together. And so we end up having a liquid in that case. And then when we get all the way over to chlorine, we have a non-polar interaction. Okay, there's still individual molecules, but since they're non-polar, they're not really attracted to one another. So we can kind of see that in the middle graph. The middle graph is looking at the melting point. So solids have a high melting point. At room temperature, we're below that high melting point. And you can see the three that we would consider ionic, metal and non-metal, those are all above the 0 mark for their melting point. And then if we look at the ones that are covalent interactions, they fall below. And the one that's kind of very close to 0 is that silicon chloride, silicon tetrachloride, because that one is a semi-metal. That's kind of in between behavior. And then the other thing we might look at is the conductivity. So you might think of, well, these aren't metals. Why would they conduct electricity? Ions can conduct electricity. So when we look at the conductivity and it says at MP, that means at its melting point. If I melt this and have molten sodium chloride, or some of these are already liquids, or if I condense down my chlorine and make it a liquid, can it conduct electricity? Well, the ions will be able to. And you can see that the first two really good ionic conductors. But that aluminum, not quite so much. We still consider aluminum a metal. You know, you worked with aluminum foil, it's shiny and all of those kinds of things, but it's not nearly as conductive as the others. Where is aluminum? It's sitting right next to those semi-metals. So that's where we're getting into that kind of in between behavior there. Okay. So the idea here is that when we have ionic interactions, we see different behaviors than when we have covalent interactions. And we can distinguish between nonpolar and polar. So we have the nonpolar chlorine as a gas and the polar ones were more liquid. And we can distinguish between the semi-metal interactions, which are sort of in between behavior, versus the very strongly ionic interactions of the alkali and alkaline earth metals. Okay, for each type of bonding, we can describe two sort of characteristics of that bonding. And that can tell us something about how the compounds might behave with those types of interactions. So we have the three types of bonding: metallic, ionic, and covalent. So the direction tells us where the electrons are going. Do they move equally in all directions, three-dimensionally, or do they stay between two atoms? You know, these two electrons are between these two particular atoms on this particular molecule. So if we have a charge, is that charge only going in one direction, the attraction of the positive only in one direction, or is it going in all directions? So for metals, remember our sea of electrons, those electrons can swish around in all directions. Conductivity works in all directions. So these are non-directional. Okay, and with an ion, the positive charge is positive equally in all directions. The negative charge is negative equally in all directions, okay? And so we end up with ions being non-directional. Now your book describes some things about ions in ways that I don't like, that make it look like they form molecules. Since they are non-directional, we end up with crystalline structures. So if I think about any one of these atoms, let's say this gray one here is a sodium. This sodium isn't any more attracted to this chlorine than it is to this chlorine. It is attracted to all of the chlorine surrounding it equally, which is why we end up with a crystal instead of individual molecules. Okay, and I'll come back to that a couple of times during this chapter as we talk about dot structures for things. All right. Our covalent bonds are the ones where the specific electrons that we're looking at, they're staying between two specific atoms. So these are directional. And so what that means is covalent doesn't tend to form these extended structures. Now I say tend to, I'm going to talk about in a second where they can. But these two tend to crystallize regardless of what's going on. Like their solid form is just going to be crystalline. Okay, and then the locality of it. Where do those electrons stay? Do they stay close to one particular atom or do they move around? Okay, in the case of metallic, that sea of electrons, those electrons swish and swash all over the place. That's the whole point of conductivity, is that the electrons are moving along that metal in one direction or another. So these are what we call delocalized. So these two in combination mean that metals are malleable. Malleable is a term that means I can pound it into flat sheets. I can spread out those atoms because I can move the atoms relative to one another without breaking a bond. Shifting these two atoms and pulling them far apart does not mean that I've broken an interaction between them because they're just sharing electrons with different atoms. And they're happy to do that. Okay, in the case of an ionic interaction, if I shift, make this visible here. If I take this positive sodium and shift it over to this position, now it's surrounded by other positive sodiums and it's not real happy about that. Okay, so that makes ionic compounds brittle. If I try to change their shape, they tend to break. All right, ionic. We said that the electrons stay very close to the more electronegative atoms, the anion. So this is highly localized. So much so that they're not even sharing those electrons. They're just staying around, say, the fluorine and not going anywhere near the cation. The covalent is localized in that the electrons stay between those two atoms and they don't tend to travel elsewhere in the molecule, but not so highly localized that they just stay on one atom. So this is localized. But not quite as much as ion. Okay, so these are some different ways that we can describe bonding. And if you look at my old exams and quizzes, sometimes I'll have questions that will say, what type of bond is highly localized and non-directional? And so you'll have to know which of these fit into that category. All right, so covalent molecules, because those interactions tend to stay in one place and they don't extend in all directions, they tend to form molecules where one molecule is discrete from the next one and so on and so forth. But if you think of a repeating pattern of covalent bonds that just keeps growing and growing, so we have like a really big molecule of these, we have a very few, but a few substances that can form really complex extended structures. And so when you hear extended structure, you should be thinking crystals. And this is one of the allotropes of carbon. Okay, so each of these little interactions here is a localized interaction between those two carbon atoms, so very difficult to break, but the structure gets bigger and bigger and bigger as the atoms connect in, each one of these has 4 bonds in 4 directions. So carbon can form a crystal structure that is very, very strong because it has this nonpolar interaction here that is highly covalent, and it moves in all directions. And so this form of carbon we call diamond. Diamond is one of the hardest substances that we know. So it is, if you've ever heard of Mohs scale of hardness, it's the top of the scale. It's number 10 on Mohs scale. Okay. Okay, so we call that kind of crystalline bonding covalent network bonding. So each individual interaction is a covalent interaction, and that means it's strong, typically stronger than an ionic interaction. But it extends in all directions, so it forms crystals like ions do. We call this an extended structure, and it is ordered. It has a pattern to it, so it's not just arbitrarily extending in all directions. Since these are covalent interactions, the interactions are very strong. These types of crystals tend to be very hard, and they are not soluble in water because we can't dissolve them to form ions that the water would be attracted to. And so you can kind of think of each crystal as being like a giant molecule. So I have a mother's ring, and my daughter born in April, her stone is a diamond. And this diamond that is clear, so I can see that it's just one piece, that is a one molecule that has, I don't know, 10 to the 15th atoms of carbon in it. So the 2 examples that we see most commonly for this are diamond, which the picture on the bottom shows just one color of atoms. So those are all carbon atoms. The picture on the top has both red and gray. And in that case, the gray is silicon. So that is silicon dioxide. We know silicon dioxide as glass if it's not ordered. But if it is highly ordered, then it is quartz. And so quartz has really a lot of interesting properties, but one of them is it's not a 10 on Mohs scale, but it's like a 7 or an 8. It's very, very hard. All right, questions about covalent bonding? So with dot structures, we are going to use dots to represent valence electrons. So this is why it's important for us to know how many valence electrons there are. So we could do this with any element. For our elements, if I'm just looking at one individual atom, we're going to mentally put an invisible square around the atomic symbol. Then we're going to place one dot for each valence electron, but each dot is going to go on a different side. Now, it doesn't matter where we start. It doesn't matter which sides have dots, but we're going to put each dot on a different side until we've used all four sides of the square. Once we have 4 dots, then we can start pairing up, okay? We're only going to pair up if we have 5 or more valence electrons. All right, so if we think about carbon, and carbon is just super important in chemistry, kind of the backbone of organic chemistry. How many valence electrons does carbon have? 4. Okay, so we could write out the electron configuration, or we could count on the periodic table in its row, the second row. There are 4 elements up to and including carbon. So that's how we come up with 4. So in order to draw carbon, I put dots all the way around carbon. I don't actually draw the square, but I kind of mentally think of there being a square so that I know when I get to 5 electrons, I have to pair them up. So this would be the dot structure for carbon. How many valence electrons does fluorine have? 7. So for fluorine, I put the 4 around, and then once I have 4, I start pairing them up. And again, it doesn't matter which ones I pair, just so long as I pair up and show the appropriate number of electrons. That might be the dot structure course. Okay, so that's the basic idea of dots for atoms. We'll get into molecules on Friday. For me, it's fine if you were to write neon's structure like this, because that is, it does have the same structure as neon, that, you know, by definition. But the reason that we separate out the last layer and don't put those inside the brackets is to show us how many valence electrons there are. So if you're doing the practice on Chem 101, it's going to want you to do helium and then 2s2, 2p6. Okay, and so this shows us that we have outside the core 6 electrons, 2 right here and 6 right here. I will ask you to make electron configurations on your quiz. So if you have not already gone back to chapter 6 and reminded yourself about how we come up with electron configurations, that should be something that you should do, and then practice that on Chem 101. So we often are not working with individual atoms. We often have ions, or we have molecules. We're going to talk about monoatomic ions first. And so there's kind of a pattern to what sort of ions might be formed. Atoms are going to gain electrons or lose electrons to try and fill out that outer shell. Now, if it's easier to lose them, it's going to try and lose everything so that the new outside shell is full. So if I look at something like fluorine, fluorine, 7 valence electrons. It's going to gain 1 electron. And we would write that as a fluoride ion, so we have a minus there. And you can also put 1 minus or -1. But to properly show the dot structure, we need to show all of the electrons. And so the proper dot structure for the anion would look like this. Okay? So for anions, we're going to show all the electrons, including the added ones. And we're going to show the charge. Now, once we get to molecules, we're going to start separating out that charge so we don't have too much notation right on top of one another. So if I were going to do that with chlorine, it might look like this. Okay, so I might put brackets around it and then put the charge on the outside. And that way I don't have that one kind of mixed in there with other stuff. We're also going to talk about formal charges, and formal charges tend to be right next to the atoms. So that's why we separate out that charge. For cations, we tend to remove all the electrons, so we don't tend to show dots. And this is for monoatomic, when I have just one atom. When we get to polyatomics, it'll be a little bit different. But if I think of like lithium has 1 dot, and I pull that electron off, I'm just going to show lithium plus, and then that electron went and did something else. Okay, so this is the dot structure for lithium. That being said, dot structures are used to represent covalent bonding. So we're not going to use our metals with the cations and all of that kind of thing very much for dot structures. So usually that's not going to be relevant, but if you were to show a cation, that's how you do it. Questions before you go? All right.